Yeah.
4 or 5 minutes just for the moment. All right. So we did not do the piecewise limit stuff. I think you will see that that is not a big deal. If you are able to figure that out on your own, great. But if you are not, no worries whatsoever. Just make sure that you go back and get some practice with that. You will have more practice with some of the other sheets that we have, but it truly is not a big deal. So I'm trying to think of what we did with piecewise, if we did anything at all with piecewise functions last year. I know that we normally do that at the very, very end of the year. So who knows? I honestly don't have a great working memory of how that played out. But just to walk you through a piecewise function in the event that you don't know what I'm talking about. So a piecewise function is a single function, okay? But it just has a bunch of different pieces. And the pieces are formed by different equations. It could be as few as 2. It could be as many as 100, 1,000, whatever. Most of the time you won't see them with more than 5 or 6 on any problem that you're doing. But this function doesn't mean that the function is a parabola, y equals that, or a line, y equals 5, or another line, y equals 7x minus 10, that are on top of each other. That wouldn't be true because then it wouldn't pass the vertical line test. So what you will see is, you'll see this open bracket. You'll never see a closed bracket on it, but you'll see an open bracket, right? And you'll say, well, the function is going to look like this, but it's only going to look like this on this section of the curve. So if you think about a big x-axis and a y-axis, for only x values that are less than 2, right? So if you had the big x and y and you went over 1, 2, everything less than that 2, you'd see this parabola. So if you think about it, you could go and just sketch a big parabola and then just keep the part where it's less than 2, which means at the very end of it, maybe put an open circle. And then to the right of it, you would just erase it. All right. And then it says to graph y equals 5, which is a horizontal line, but you're going to only graph that when x equals 2. So if you think about it, you could draw a big horizontal line, y equals 5, and then go back and keep it where x is 2. So where x is 2, you could go up there at that 5 and keep that dot. But everything else you'd have to erase, which would leave you with just a what? Just a point. And then right here, you have this line, which starts down there at -10, which has a slope of 7. You could graph the whole thing if you want, but where are you going to keep the graph? Only to the right of 2. So I guess you could draw the whole line if you wanted to, but then you'd go and say, all right, here's x equals 2. I'm going to look up there, which would lead, I guess you'd be at +4 at that point, right? When x is 2, the y is 14 minus 10 or 4. You could go up to that point and put an open circle and then erase the rest of it and keep the part of the graph looking like this. But I don't want to graph it, okay? But that's the idea of what you would do with a piecewise function. What I want to do is just answer the questions. So if you think about a limit, so far on all the graphs we've done, is everybody with me? On all the graphs we've been dealing with, we've been looking at a limit, and a limit makes you look from what? Both sides. Now, if I were to ask you what the limit is as x approaches -4, well, you think about where -4 is. -4 is way to the left of 2, isn't it? So it's basically right in the middle of this line, not in the middle, because there really is no middle, it goes forever. But it's not at the edge, right? It's kind of in the whole interval of what's going to exist on this line. Well, if that's the case, I can just plug it in, because we know that parabolas don't have holes, do they? And they don't have vertical asymptotes because it's a polynomial. So I can treat it like a normal limit if it exists not at that endpoint. If it's basically in the interior of the region. Now, if I ask you for the limit as x approaches 8, well, I'm not going to look here because this graph only exists less than 2. And I'm certainly not going to look here because this exists at 2. 8 is bigger than 2, isn't it? So I'm going to use that function to find my limit. And because 8 is not at the end point of that section or that segment, it's right there in the interior of it, and it's a line, and lines don't have holes or vertical asymptotes to mess me up, I can just plug the 8 in there and get my limit. Is that making sense? So anytime I ask you for a limit, as x approaches a value, if that value is in the interior of one of these regions, if it is, I don't have to worry about much except plugging it in. Hey. You can Anderson rules.
That can be my rule, not like mathematical rule.
Just
Tardy rule.
Yeah, if you're within 50 minutes of the start of class, you're technically on time.
Newton's theorem.
That's right. Ignore tardies all the time. Okay, so really, a piecewise limit, don't be frightened by it. If I ever look at the value, and the value is not at the end point or at the end of the little segment where the graph exists, then treat it just like you would if it was a regular function. So for values like -4, which are clearly to the left of 2, or 8, which are clearly to the right of 2, then you don't, or even infinities. Negative infinity, that's definitely less than 2, right? So literally, when I see that, I'm treating it like it was just like this was right there. The issue for you will be what happens when it happens at one of these points, where it breaks. Well, that's different because this graph, from one side, it might be going to here, right? Like for this parabola. To the left of 2, it might look like this. And then at 2, it might be up here. And then to the right of 2, it might be down here. We don't know exactly what the graph's going to look like because we don't have a picture of it. And honestly, I don't really want to draw these. All right, that requires me to complete the square and do all kinds of weird stuff. So what I'm going to do is just stick to my rules with limits. And limits say, we don't care what happens at 2. Right? Limits don't care what happens at 2. They care about what happens as you do what? Approach 2. So if I were to say, what is the limit as x approaches 2? This is the piecewise question that really is in play here. Because what I'm going to do is to check the limit as x approaches 2, who cares about what it's equal to? Okay, we don't care. We care about what happens from the left and the right. So how do I check a limit from the left? Well, we've been doing that. We just plug it in and see what happens, right? Right? And now, if I get an asymptote there, like if I get like 5/0, and I find out that there's a vertical asymptote, well, we learned a couple days ago about what to do with those. You got to check really close to see which way it's going. But I'm first going to check and just see what happens. I always do that, unless it's an infinity where I can't technically plug it in, and then I use my infinity rules. So at 2, I'm going to go, well, how do I check from the left? Well, which function shows up to the left of 2? That first one, right? Because it's less than 2. Well, plug a 2 in. Plug a 2 in, you get 3 times 4 is 12, minus 8 is 4. So that means that this graph is approaching 4. It's not equal to 4. Who cares what it's equal? But it's approaching 4 from which side? From the left. So then you go and check, well, what's happening from the right side? So you take that 2, which equation represents the right side of this function? The bottom one. Plug a 2 there, and you get 14 minus 10, which is also 4. So if those two values are the same, that means this parabola was approaching 4, this line was approaching 4, and if they're both approaching the same value, then the limit exists, and its value would be 4. That's how you deal with piecewise limits. You just got to check both sides. But never, ever do you even care about what happens when it's equal to 2. All right, so this graph probably looks something like this. Like at x equals 2, and I don't know exactly, I just know because I don't care too much, but I know that it's a parabola looking something like that from one side, right? It's a line looking like that from the other side, but at 2, it's actually up here at 5. So the graph kind of looks like that, but you can see that from the left and the right, it was approaching a height of 4. Do y'all see that? Because I checked from the left with the parabola, from the right with the line. But my goal for you is to be able to do that without graphing it, because we don't have the time to graph these. Are y'all seeing that? Now, if it's not a piecewise function, because I know the behaviors of graphs don't, by the way, let me take that back. So sometimes the graph is going to do this, right? You're going to check from the left and you're going to get 4. You're going to check from the right and you're going to get 6. And you're going to say, oh, well, the limit doesn't exist. The value might exist, but the limit doesn't exist. And that's okay, right? But a lot of times the values are going to equal. This kind of behavior never happens with polynomials. You never have a polynomial that goes to here and then just hops up to a value and continues, do you? Right? You don't have any breaks in polynomials. This kind of behavior doesn't happen with rational functions, does it? The only thing that could possibly happen with a rational function that's weird is a what? It's not even that weird. Asymptotes or holes. So this is called a jump right here, where the y values literally hop from one to another and then continue. All right, whether there's a point or not in there, that's called a jump. Now, if it hops over here, that we don't call those jumps because there's this void of x values that never existed. But if it literally, as it's approaching 2, it gets to here and then it hops up at 2 and then continues, we call that a jump. We call it a jump discontinuity, technically, and we'll talk about discontinuities or continuity today. Are you with me on this? So all these other ones, this one, this one, this one, this one, because they don't occur at these breakpoints, I can treat them just like regular limits. So right here, as x approaches -4, I go, well, -4 is in this interval. I'm just going to plug a -4 in there. I get 48 plus 16 is what, 54? 64? So tell me if I'm wrong. So I think my limit is 64 there. As x approaches 8, 8 is clearly in the midst of that interval. I plug an 8 in there. 56 minus 10 is 46. Again, correct me if I make a careless error. X approaches negative infinity. Negative infinity is way to the left there. Well, what's happening on this parabola? What does it look like? What's a parabola with a positive 3 with the highest power? It does what? Up to the right, and since it's an even power, also up to the left. So what's the limit of this function as I go to negative infinity? Positive infinity, isn't it? So I'm using what I know about these. And then this one says, all right, what happens as you go to positive infinity? That's that line. What happens to this 7x minus 10 as you head to the right? Going up to positive infinity? All of these I can treat like just regular functions because I don't have to check left and right because they don't break at that value. This is the one that I had to treat. And because the limit was the same from both sides, it had a value. Y'all with me on that so far? But the only time I would even care about that, can anybody tell me? When would I even care about this right here? Good. If I were to say, what is f of 2? Then I'm asking you what the value is at 2. And I would go, oh yeah, f at 2 is just 5. Does that make sense? So remember, limits don't care about equal. They care about approaching it, getting closer and closer to that value. So let's just look at a couple of these. And I'm really kind of helping you along on these on number 12 and 13. I'm asking you to check from the left and check from the right, and then tell me what the limit is at 2. So I'm giving you some practice, but on a test, I'll probably just ask you this. But if I ask you, what's the limit of this function as I approach 2, what are you going to have to do? Check from the left and check from the right. Because that's what you have to do on piecewise functions. Because they might be doing different things, right? It's totally two different parts of the graph. So let's check it out. 2 from the left. Which equation? First, second, or top or bottom or middle? Top. So if I plug a 2 into there, what do I get? 1. And remember, don't plug in 1.999. When would I plug in 1.999? When's the only time I would care about doing that? If there's a vertical asymptote, right? And I'm trying to figure out which way it's going. I'm trying to get really close. So don't do that, even though it says from the left. Whether it says left or right, who cares? Plug the number in and see what happens. Because very likely you'll get an answer and we're good. It's only when you get a VA that you have to go, okay, let me check really close to see which way it's going. So I plug a 2 in there and I get 1. Great. My limit from the left is 1. What's my limit from the right? Which equation? Top, middle, or bottom? Bottom. Plug a 2 in there and I get 2 over 2, which is 1. So what does that tell me? That the limit does exist. So yes, it does. And what is it? 1. And that's it for a piecewise function. You'll do this all day long. But who even cares about what happens at 2? That's this question. F of 2 is 2. f of 6. I guess I would use that interval, right? Because 6 is bigger than 6 over 2 is 3. These care about what happens when it's equal, but limits care about what happens when it approaches. And if it breaks at that value, you got to check left and right. Now, AP sometimes will mess with you. They'll do things like this. Like instead of saying less than, greater than, sometimes they'll do this. Equal, not equal. What do you think not equal means? So what does that mean? That would mean left and right. So if you have, I don't do that a lot with you guys in this course, but AP likes doing that on the AP test, on a limit. So if you see this, this is just the same thing as me saying x less than 1, x greater than 1. So it's like me giving you both inequalities. So this is basically saying that this graph is going to behave everywhere except here. Here, at 1, maybe I do that. But that's not this problem. I was just throwing that out there. So if you see it, you're not bothered by it. So let's check this limit. What's the limit as I approach the function from the left side? What do? Plug 1 in where? Top equation. And when I do that, I get 1 over 0. What does it mean when I get 1 over 0? It's not my answer. It means a VA. So since there's a VA and I'm coming in from the left, I need to know which way it's going, don't I? So how do I do that? That's when I plug in really close to 1 from the left side. So maybe like 0.9. So if I plug a 0.9 right there, what do I get? A negative number. Now I'm still going to get really close to 1. Remember that we did this. I'm still going to get really close to 1 on the top. So that's positive. And I'm going to get really close to 0 on the bottom, but it's going to be negative. So it's a negative number that's really small. So what does that mean about this limit? It must be going negative infinity because you already know there's an asymptote there, right? So none of these are your answers, they're just your thought processes. So I must be going to negative infinity from the left. Now what about from the right? You going to plug in 1.1? No, not yet. We don't even know if there's an asymptote. I'm going to plug in 1, and I get 1, and 5 is 6, minus 2 is 4. So I don't have to check plug in 1.1. So it basically is diving on the left, but it's approaching the number 4 from the right somehow with a cubic or something. Does the limit exist there? No. So does the limit exist? No. And why or why not? If you had to explain that, what would you say? Yeah, you could say the limit from the left and the limit from the right are not equal, or basically negative infinity would not be equal to that positive 4. All right. And then lastly, what would f of 1 be? Yeah, plug it in where it's equal 1. That gives you a 4. And what would f of negative 1 be? Plug a negative 1 in there, and you get negative 1/2. Y'all seeing these? Okay, couple of comments on some of these, and I gave you some square root problems. I wanted to address those because we haven't talked about those yet. And these can be a little tricky. They're really simple once you get the hang of them. And here's what I need you to know. Do you remember absolute value? What the definition right over here. The definition of absolute value, it literally is written on your calculator. Like on your calculator, if you look at it, the little book button, the left side of your book button, it says absolute value of x. It has an x and a negative x. That's literally, the absolute value is a piecewise function. It literally means, but it tells, I don't know if it has the entire, no, actually it doesn't even say that. It says absolute value of a box equals box. But the idea is this. Absolute value means it's going to look like this is a function. It's going to look like y equals x part of the time, and it's going to look like y equals negative x the other part of the time. It's a piecewise function. And that's the idea on absolute value. Your very first week in my class last year, I don't know if you remember this with absolute value. Did you remember what we did when we had an absolute value in our equation? We said sometimes it's positive and sometimes it's negative, right? Sometimes it's positive, sometimes it's negative. So what we're going to do is apply that thinking whenever we're doing a limit. For instance, look at numbers 15a and 15b. 15a says, what's the limit as I approach infinity? So my thinking is, oh, I've got some infinity rules. Great, right? What are my infinity rules? When the power is bigger on the top, then what do? I basically look at the signs of the highest powers, and I like plug in a big negative number and see what I would get, either positive or negative, and that tells me which direction I'm going. If the powers are the same, what would I do? Take the coefficients of the highest powers and call it a day. And if the power's bigger on the bottom, what do? It's always 0. So I've got rules. Problem is, I got this square root in there. Well, what do you think is going to happen if I square root something with an x squared? Now, you're used to saying x, but is that really true? I thought square root of x was that. You remember this? I'm sorry. Square root of x squared is that. Do you remember solving problems like this? X squared equals 4. And when you square rooted both sides, a lot of you just jumped straight to this, right? And you kind of learned that in Algebra 1. At the beginning of the year, I told you the problem with that thinking is it makes you think that the square root of 4 is plus or minus 2. It's not. Square root of 4 is 2. Ask your calculator. The calculator never says plus or minus 2. It just says 2, because it is 2. So where does that come from? Well, it comes from the square root of x squared really being absolute value of x, the square root of 4 being 2, and then saying sometimes x is positive and equal to 2, and sometimes x is negative and equal to 2, and the net result is plus or minus 2. People just skip this step, but we can't when we're doing a limit. So if I want to apply my rules that I know about powers, I got to get rid of this square root. So let me ask you a question. What do you think the square root of an x squared is going to give you? The square root of x squared is going to give you what? An absolute value of x something. I don't know how that's going to break up, but it's going to be x equals something. So check it out. I mean, absolute value of x something. So I'm going to rewrite this as this. Absolute value of x something. Because I don't know what times what gives me that. Because it's got that minus 2 on there. But here's the great thing. I don't care. And the reason I don't care is because all I'm concerned with when I do powers, when I have infinities, are the highest powers. So I'm not going to care about all this other junk anyway, am I? Now, how do you think I deal with positive? I mean, how do you think I deal with the infinity? I can't ignore it. It's there. It gets in the way of me using my rules, because my rules from yesterday's infinity problems did not have any absolute value in them. Well, that's where I go to this. Sometimes it's infinity. I'm sorry, sometimes it's going to be positive x. Sometimes it's going to be negative x. Well, guess when it's positive x? When I'm heading to infinity. Guess when it's negative x? When I'm heading to the left, negative infinity. Which way are you heading? To infinity. So if I'm heading to infinity, then I can just completely ignore the absolute value. And if I can completely ignore the absolute value, what do I end up with? What do I end up with for this since my powers are now the same? 3 over 1, which is 3. Now, look at part B. Part B, you look at this and you're like, oh, infinity, I've got rules for that. Oh, crap, the square root's in the way. Well, what's the square root of an x squared? Absolute value of x. So I can replace this with the absolute value of x something. But again, I don't care about that extra stuff because all I care about is the highest power. Right? Yes, no? But this time I'm going to the left. If I'm going to the left, what do? I negate the stuff. So that would mean that this to negative infinity becomes 3x plus 7 over the negative of that. But again, I don't care about all that, do I? So now I've gotten rid of the square root. I've gotten rid of the absolute value based on which direction I was taking the limit. And now, what's the limit of any time you have the same powers? Take the coefficients. 3 over negative 1, negative 3. Sorry, I got all this other junk in your way. Y'all seeing those? Now, the great part of it, what happens, do you think, when you hit, surely I have one here. Yeah.
So why, if x is negative infinity and it's in the absolute value, why didn't it just end up being positive?
Because, oh, I know what you're thinking. Remember my rules. The only time I'm going to actually have to plug in a big number is when the power's bigger on the top. When the power's bigger on the top, I've got to see which way it's going, right? It's either going up or it's going down. But when the powers are the same, it's a horizontal asymptote, right? It's not going up or going down. It's going at the horizontal asymptote. And what is that horizontal asymptote? The coefficients. Now, had this end up being this, then I would have cleaned it up just like we did, and I would have said, okay, now I need to plug that negative in there. And when I plug that negative in there, I get +3, right, over a positive number. Okay, this must be going to positive infinity. But because these powers are the same, my rules are take the coefficients. Those are the rules. Because this has a horizontal asymptote, I just need to find that horizontal asymptote. See, I don't want to plug an infinity in there and go, all right, if I plug a negative infinity in there, I get a negative number there. Plug an infinity in there, I get a positive number there. And then say negative infinity. If I do that, I've missed this problem because this problem isn't going up or down. Now, I can find the sign that way, but this is a horizontal asymptote, right? Horizontal asymptotes occur when the powers are the same or the power is bigger on the bottom. The only time I need to check where the power, whether it's positive or negative, is when the power ends up being bigger on the top, because I know it's doing this or this, and I got to know which way. But I don't really have to worry about any of that at all. All I got to do is look at the coefficients, 3 over -1, because I know this has a horizontal. Does that make sense?
It's more like, why isn't the x on the bottom positive since it was absolute value?
Because remember how absolute value sometimes looks like that and sometimes looks like that? So if I'm heading to negative infinity, I have to, this is absolute value of x. I have to use the negative version of that because I'm heading left. So I have to replace the absolute value of x with the negative x. If I'm going to positive infinity, which is this way, then I've got to replace absolute value of x with a positive x. Does that make sense? So I'm just following my rules of absolute value to replace this expression with what it's equal to in that direction. Right? And remember, sometimes absolute value is a negative number, because for a negative x's, when I take the negative x and plug it in there, the two negatives make it positive, which is what's supposed to happen. So it has two different parts. Absolute values are essentially piecewise functions. So you have to decide which piece you're working with. So if it ever goes left, use the negative version. If it ever goes right, use the positive version. And that way you can get it to a fraction that has just x, no absolute value, no square root, and you can use your infinity rules like you learned yesterday. Now, what if it's a cube root? What's a cube? I'm sorry, what if it's a cube root right here? If it's a cube root, does a cube root of x cubed have an absolute value in it? Does a cube root of x cubed have an absolute value? No, what's it equal to? Just x. So those clean up really nicely. You see a cube root of something, just put x something, and then you're finished with it. Now, when you look at the way a college professor will teach this, they'll teach it slightly different, but at the very end of the day, they're still going to, every time, say, okay, if I'm heading to the right, use the positive version. If I'm heading to the left, use the negative version. Except the only difference is they're going to simplify each of these using these weird rules I talked about yesterday. Remember these? So that's what they're going to do. They're going to clean all of them up using these weird rules. And to me, it makes it a lot trickier than what I'm showing you. So that's why I kind of teach it from a different perspective. Are y'all with me on the piecewise function thing? So I put a bunch of other stuff in here. let me just talk about one more. Look at number 27. All right, I have this function. It's a piecewise function. Stay with me. So this is actually an AP question. I've changed numbers or maybe something. But this question says, for what value of A will this limit exist? Now, I'm saying, well, the limit as x approaches -1. So what has to happen for this to actually have a limit, a value to actually exist as I approach -1? What does that mean? Somebody be a hero. So these two functions would have to, as they're coming in towards -1, would have to meet at the same value, right? There may not be a value there, but they have to be approaching that same value. Do you know what this first equation is? What do those look like? X cubed. Little wiggle, right? Like this, maybe? What does that look like? That's just a line. What does the A represent? Just the constant, like the y-intercept in this case? Y'all seeing that? Now, I don't know what that A is, but I can probably see what they're doing and think about that at the same time. So how would I see if this limit exists? If the limit exists, then the limit of the function as x approaches -1 from the left would have to what? Equal the limit of the function as x approaches -1 from the right. So let's check it out. From the left, I use the top equation. What happens when you plug a -1 in there? You get -1 plus 4 is 3. All right, limit from the left is 3. What happens when you check -1 from the right? You plug it where? There. What do you get? -2 plus A. So if these two limits are the same, then the limit would exist, right? So what does A have to be for that to happen? Yeah, so you just add 2. A would have to be 5. So when A is 5, the limits are equal. That literally is an AP question. Now they'll start making it a little uglier and start asking about continuity or differentiability, things like that as well, which we're going to start with continuity today. So the rest of this stuff is just practice for you. Hopefully you are able to do everything except the piecewise function stuff, or at least a good bit of it. There were a couple of things with the square roots like this 42 and 43. You're not able to do those. Go back and redo those based on your newfound knowledge, right? Each of these square root of x squared gives me what? As you're simplifying, what's the square root of x squared blah give me? Absolute value of x blah, right? And if I'm heading to infinity, what do I use? The positive of that. So look, now I've got a problem I can do. Same powers, use the coefficients. You tracking with me? Like here on part B, square root of x squared something is going to give me absolute value of x something. But this time I'm heading left. What happens when I head left? I use the negative version of that, right? So up, same powers, use the coefficients. Do I have to worry about that with cube root of x cubes? There's no absolute value. Just change it to an x something, use your coefficients. All right, let's talk about continuity because we're running out of time. So continuity is one of the more common questions that's asked, and people make this really ugly. Let me ask you a question. If I were to draw a function that looks like this, would you say that it is continuous? If I were to draw a function that looks like this, would you say, based on your knowledge of the word continuity, would you say that this function is a continuous function? Yeah, based on your limited knowledge of the word continuous. Continuous sounds like there's no breaks, right? It continues. This is a continuous function over the entire domain. Okay? Now, would this be a continuous function? No. There's a break in it. Would this be a continuous function? No. Now, the domain is all reals because every x value has a y value, but it's not continuous because you had to stop, move up to another point, come back. So when you think continuity, think, if I can take my pen and start at negative infinity and end up at positive infinity without ever lifting it off the paper, And what I mean off the paper, I don't mean this, like, well, you could definitely go around the hole and then back. Technically, a hole means what? There's nothing there. So you would have to hop over, wouldn't you? So if you could continually go, then it's continuous. You tracking with me? Now, the problem is, what happens when I don't see a picture of the graph? Now, by the way, you can be continuous on certain intervals, like right here. I can be continuous from negative infinity to 2. Are there any breaks from negative infinity to 2? No, and I have it open at 2, which does not include 2, right? Is it continuous from negative infinity to 8? No, because there's a break at 2. And breaks can happen like this. This is called it's actually called a replaceable discontinuity, or a removable discontinuity. And it's called a removable discontinuity because I could remove it by putting a hole in there, even though you don't do that. Holes are called removable discontinuities. You could also have a jump discontinuity. A jump looks something like that. That can only happen with what kind of functions? Piecewise functions. You could also have an infinite discontinuity. An infinite discontinuity occurs at an asymptote, like that. So removable, jump, or infinite discontinuities, or discontinuities that may happen. Also, the graph might just end. Like it could just stop right there and then maybe pick up somewhere else. And there's just this space right here, this void, right, of emptiness, right? It's not continuous there. It doesn't have a special name. So all of these things are great, and we know if it's discontinuous there, we can look at it and see that. The problem is what happens when I can't see it because I don't have a nice, lovely picture. All I have is a function. Well, if I have a function, the way we go about that is through these 3 checks. And they make really good sense if you think about them, but we'll go through a few of them. So the first thing that has to happen to be continuous, and you have to know these 3. My calculus kids are going to walk in here at 9:50, and one of their test questions is worth 3. Is it discontinuous or why is it continuous? And you have to list these 3. So the 3 continuities, this is in words, but this is what I'm basically saying is, what is that saying right there? F of A exists. That means that at this particular value, oh, by the way, sometimes I don't ask you if the whole function is continuous. I ask you if it's continuous at a certain value. And to be continuous at a certain value, like if I had a function like this, this function is continuous on a lot of intervals, right? All these intervals are continuous, but at these certain values, like at that A value or at that B value, or whatever they are, it's not continuous there, is it? So to be continuous, the value has to exist there. Clearly, at vertical asymptotes and holes, there's no value, is there? And even if there is a value, right, it'll get eliminated by another rule. So the first thing you do is you make sure that something actually exists there, that there's some Y value. If there is, great, you've checked off the first point of continuity. The second point is the limit has to exist. You don't have to say is a real number. You could just say it exists also. And you can see right here, clearly that limit, let me give you another one right here. Clearly that limit does not exist right here, does it? But even though the value did, the limit did not. Now here the value exists, right? Because there's a point there, but the limit existed also, right? So that actually checked 2 of the boxes. The last box is the value that you got when you checked the value has to equal the value you got when you checked the limit. And that doesn't happen here, does it? Because maybe the limit was 3, the value is 4, that's not equal. So to be continuous, the value has to exist, the limit has to exist, and they have to be the same thing, which is kind of common sense if you think about it, right? You got to have a point there, and it's got to be going into that same point from both sides. Those are the 3 points you check. Now, that seems pretty obvious, but again, it's not always that obvious when you don't know what the graph looks like. So you have to pull out your rules. So let's check continuity with a couple of these and see if you can make sense of it. All right? And those are the discontinuities I was talking about discontinuities, meaning there is no continuity at that value. So let's just check a couple of these. Looking at this picture right here, the limit as I approach -6. 1, 2, 3, 4, 5, 6. This is -6 right there. Now, do you think it's continuous right there? Yeah, it's going right through that point. But think about it. The value exists. It's 0. The limit from the left and the limit from the right exist. That's 0. And the value and the limit are the same. Checked off all 3 points. So the limit existed right here. It was 0. The value existed. It was 0. And because they're the same, then yes, it is continuous. I'm checking the points of continuity. Now let's check at -2. Here's -2. Does the limit exist here at -2? Yeah. From the left and the right, what's the limit? 2. So the limit existed. Does the value exist at -2? Yes, it's what? -2. The value existed. The value existed, the limit existed. But were they equal? No. So is it continuous? No. Now you can visually see that it's not continuous, right? You had to go to here, pick up your pen, mark this one in, pick up your pen again, jump back there and finish. So at that point, it's clearly not continuous there. But again, you can see the picture. When you can't see it, it might be a little trickier. Let's do one more. What about this? Does the limit exist at 0? No. It's going to 3 from the left, 1 from the right. So right there, the limit does not exist. I can go ahead and say, no, this is not continuous right there. Even though the value does at 1, if any one of the 3 rules is broken, you're out. What about 3? Does the limit exist? No, there's a VA, they're going in different directions. Does the value exist? No. Now don't look at these and go, oh, look, they're both D and E. That's the same thing. So it's continuous. Don't do that, all right? They're both D and E's, right? So definitely no. And what about here over here at 7? Does the limit exist? Yeah. Now be careful. I have an answer. It's approaching -infinity, but what does -infinity mean? D and E. So did the limit exist? No. So right there, no, then definitely no. And f of 7 did not exist. But remember, D and E is in that in -infinity conversation. So if I ask you, where is this graph continuous? Did it look continuous as I was going from here all the way to -2? Did it? Were there any breaks, jumps, anything? So from -infinity to -2, it looked continuous. Leave that open. Then from what to what? -2 to 0. But not at 0, because you just checked at 0 and look, at 0, no. And then from 0 to 3, it looked pretty good. But what about at 3? No. And then from 3 to 7, it looked pretty good. But what about at 7? You checked it. No. And then it looks like 7 to infinity, it looks pretty good. And I'm always going to have parentheses on those if I'm talking about continuity.
You put the U.
I can put U or I can put commas. AP lets you put commas. Okay, so I'm going to probably run out of time. You know what I'm going to do? I'm going to keep talking on this video for about 5 minutes. So when you go home to watch that trig one, I want you to go to the very end of this video and watch the last 5 minutes. Are y'all with me? Because the last 5 minutes, I'm going to keep talking, but I could talk about one of these when you don't have the picture. So when the bell rings, feel free to walk out the door, but I'm going to keep talking. So scroll to the very last 5. All right?
That's the band.
It might not even be 5 minutes.
That's one of the pencils with the bouncy leg. That's from the book. Do you not remember that?
Hey, y'all have a great break. Right.
My brother's really sad. He comes into town today and he wanted to sneak into the school tomorrow, but we haven't.
Yeah.
Well, we're not here.
It comes into town today?
Yes.
What time?
I don't know, but he's coming to the boys' soccer game.
Come on, say what?
Yes, sir.
All right, so last 5 minutes, okay? Just give me 5. So clearly, I don't have a picture of this, right? And if I don't have a picture of this function, I still have to answer questions about continuity. So let's remember our points of continuity. The value has to exist. The limit has to exist from both sides. I know how to check that now because I've talked about piecewise functions, and they have to be equal. So let's take a look at this. Number 17. Ultimately, here's my question. I want to know, is the function continuous? But to do that, I've got to check the 3 points of continuity. What are they? Does the limit exist? That's one of them. Well, to do a limit on a piecewise function, you have to check from the left and from the right. So let's go ahead and do that to see if the limit exists. So from the left of -3, here's -3, there's left, I get 1. Okay, so from the left, I get 1. From the right side of -3, that is this equation, bigger than -3. I plug it in there and I get 27 minus 26, also 1. So because the limit from the left and the right were equal, the limit exists. That's one of my 3 points of continuity that I have to check. And the rules of continuity, you could call it. Now the second rule was, or first, depending on which order you're going, does the value exist there? Well, where is f equal to -3? There's an equal sign. So it's equal to -3, also at 27 minus 26, which is 1. So there's another rule that's checked off. And because the limit and the value are the same, then it is continuous. Yes. So that means that I know now that this piecewise function, where this line hits this parabola, comes in and connects. And it connects and fills in the hole. It fills in the hole. It approaches the same from both sides, and the hole and what it's approaching are the same. So this parabola connects with this hole so that you never have to pick your pen up. All right? You have checked at -3. Now, let's check at 2. So at 2, is the graph continuous? Now, I'm not going to write up all these questions this time. I'm just jumping straight to the thing I really wanted to know, and that's continuity. But I've got to check the same things. So let's check the limit. From the left of 2, I get 12 minus 26 is -14. So the limit of the function as x approaches 2 from the left, -14. From the right side of 2, plug a 2 in there. 2 over 2 is 1. 1 minus 15 is also -14. The limit of the function as x approaches 2 from the right side, also -14. So the limit of the function as x approaches 2 exists because it's the same from the left and the right. That is my first check. Now, does the value exist at 2? That's what it's equal to. Yes, f of 2 was 10. So the value existed. But were they equal? No. What that means is, even though the graph approached the same value, the actual value was not in the same place. One was down here at -14. The value is up here at 10. So it looks like there's a hole there with a point above it. That's not continuous. So is the function continuous at 2? No. So I know there's a break at 2. Then I go to 6. That's it. That's the other break point. So I go to 6 and I go check the whole thing again. What's the limit of the function as I approach 6 from the left, 6 from the right, 6 and 6. And I'm going to check the same way. So as I approach 6 from the right, from the left, that is here, 3 minus 15, -12. 6 from the right, -18 plus 6, -12. The limit does exist, yes. Does the value exist? There's no equal. So since that's a DNE right here, this breaks the rule right now. Well, if it breaks it, then you're done checking. If any one of the 3 rules breaks, it's not continuous. So not continuous is 0. Now, the very last thing you got to check is, are there any places in the graph where there's a hole or a BA? Well, none of these are rational functions, right? There's no x in the denominator. There's nothing really to give you an undefined. There's no square roots where x could be negative. There's no other messed up situation. So you really don't have to worry about any other places. But in this case, you know that it's not continuous there. So if I ask you, I also asked you at 0. This was 6. I asked you about 0 and 15 just randomly. We'll go ahead and answer that. 0 is in this interval. So since it's in the interval, it's not really broken at that. I can just plug a 0 in there. Or you can ask yourself, wait a minute. In between -3 and 2, it's a parabola. Parabolas don't have any breaks. There's no breaks in between -3 and 2, then 0 is going to be fine. So yeah, of course it is. Or here at 15. 15 is way to the right of 6. That's a line. Lines don't have breaks. If there's no breaks, of course it's continuous there. The things that you're worried about are these break points, right? You're worried about where it breaks. Or maybe if there's some place on this function where there's an x in the denominator, giving you a hole or a vertical asymptote, you're worried about that kind of stuff too. But in this case, I had a no here and I had a no at 2 and I had a no at 6. So if I want to know where it's continuous, I have checked everywhere that I possibly need to check. So I'm going to say everywhere except -infinity, not at 2, and not at 6. But everywhere else, it's good. So basically, this accounts for it not being continuous there. This accounts for it not being continuous there. Actually, I shouldn't say not equal to. I should say this accounts for not being continuous there. This accounts for not being continuous there. And you can put unions, but AP usually puts commas. All right? Thanks, guys. Have a great spring break. Don't forget to watch the next video on trig limits. It's very important. Have a good one.